We're now going to look at the most effective method for solder joint removal: solder extraction, using controlled heat and continuous vacuum. This is a handpiece of a typical solder extraction system. It has a hollow tip and is heated by an element within the shroud. Behind the tip is a heat transfer tube and a receiving chamber where the waste solder is collected and solidified. A variety of power sources are available to provide vacuum and allow you to control the temperature level of the tip. Let's see it in use. The heated tip is put down over the joint, and when solder melt is observed, the vacuum is started and draws out the solder from the joint and deposits it into the chamber. If the lead has been pre-cut, it too can be drawn into the chamber. The continuous vacuum first extracts the solder and then pulls cool air through the hole and across the surface of the pad, cooling the work and the tip. Moving the lead is a key part of the method. It signals a complete solder melt and when to apply the vacuum. Sweat joints don't have a chance to form within the hole since the lead is kept moving during cooling. Looking from the circuit side of the board, here's what happens at an individual joint. The tip comes down hot and begins driving its heat into the joint. Then the lead movement is started. As the melt begins, the tip rides on a lubricant of molten solder and never actually touches the pad. When the melt is all the way through, the lead can be felt swinging free. Then vacuum is started, and out goes the solder, followed by a high-velocity flow of air. It cools both the work and the tip well below solder melt temperature. When the tip's removed and vacuum stopped, heat is instantly driven back in, and the tip is ready for the next lead. After all leads have been desoldered, the part is completely free and can be easily removed. The board is undamaged, and the holes are clean and ready for the replacement. Solder extraction is the only consistent method for dealing with the resweat problem in plated through-hole solder joints. If you're dealing with double-sided or multi-layer boards, it's the method of choice, since it's applicable to any type of solder joint regardless of board configuration. Let's look more closely at how the extractor is used on various types of joints. First, the tip size itself must be determined. They come in various sizes designed to handle different sized joints and component leads. A good technique is to first check the fit of the tip by placing it over the lead to ensure that it's the right size for the solder joint. The proper size tip should have an inside diameter small enough to permit good heat transfer to the lead or pin, but with enough clearance to let molten solder and air pass up through it easily. The outside diameter of the tip should be no larger than the pad diameter, so that it will not touch the circuit board base material. The handpiece is held like a pencil, with the tip at approximately a right angle to the board. This angle ensures you get proper heat transfer and maximum vacuum flow through the board. No more pressure should be used than you'd get from the weight of a pencil balanced on its point. Once the melting action starts and the tip comes down over the lead, the tip is wiggled until the lead swings freely and easily. This indicates full solder melt. Since the leads on this component are round, the tip moves the lead in a circular motion. In this case, the components are dual inline packs with flat leads, so the tip is moved back and forth along the flat plane of the lead. Notice how the corner leads are done first, and then every other lead. This technique prevents heat from building up in any one area and reduces the possibility of lifting circuits. A good practice when you're extracting is to watch for solder melt here on the component side. The melt is our workpiece indicator during extraction and tells us when to start the vacuum. By watching the joints on this side, we can see it happen. At the same time, we feel it happen on the circuit side. Sometimes you may need to extract joints that are heavily coated with oxides. In many cases, if you first cover the joints with some liquid flux, you'll be able to desolder them quite easily. A major advantage of this type of solder extraction is that it's performed on a lead-by-lead basis. This lets you take into account the individual thermal mass properties of the joint. Before you start, you should always examine the joint to see how much mass is there. At some joints, you may have only the pad and lead. Some may be connected to one or more circuit runs. And at others, there may be large surface ground planes, buses, or large solder masses. Another thing to look for is the amount of solder in the joint. You need an adequate fillet to get good heat transfer for complete melt-through. If there's insufficient solder to begin with, then it's best to add solder before attempting to desolder. Joints with large thermal mass often present a problem. This one, for example, may take much longer than the recommended 2 to 3 seconds to fully melt, since it's connected to a large voltage plane. In cases like this, and particularly with multi-layer boards, the tip temperature is first increased to see if that alone can provide a complete melt within 3 or 4 seconds. It does on the lower mass joints. But on this one, it doesn't. The large thermal mass of the voltage plane dissipates the heat too rapidly to allow a complete solder melt to occur, and even repeated attempts will not succeed. There's still solder left in the hole. Auxiliary heat is going to be needed, so the holes will first be resoldered. This will ensure a good heat transfer. Now the board is repositioned so that both sides are accessible. The iron is then applied to the lead on the component side, followed by the extractor tip on the circuit side. The two heat sources permit balanced heating of the joint, and full solder melt occurs in an acceptable time period. The holes are left clean and free of solder. On this board, auxiliary heat will be required to remove a connector. It's small, with recessed pins, so a resistance tweezer will be used. It can grip each of the pins and heat them. They're so close together, an extractor tip is put on them first, then the tweezer attached. Heat's applied for 2 to 3 seconds, and then the extractor put on the joint on the circuit side. After the last lead's done, the connector comes off easily. The joints can be desoldered within 3 seconds this way. The thing to remember here is that the amount of auxiliary heat needs to be controlled and timed to just a few seconds. And you need to place the heat at the point of maximum thermal mass. The recommended procedure is to apply the auxiliary heat first for about 2 or 3 seconds, and then apply the extractor tip to the lead. As soon as you feel the lead move freely, apply the vacuum and remove the auxiliary heat. With sockets like these, auxiliary heat can be applied with a small tip soldering iron. Then the desoldering tip is placed over the lead, and the joint is desoldered. Removal is rapid and clean. For an IC socket, a small pin or piece of metal can be used. It's inserted into the socket, then the resistance tweezer used to apply the heat. Again, the part comes out easily, with the holes left clean. So far, all the leads we've dealt with have been unclinched. What about the clinched ones? The first thing to do is to remove at least the surface solder from around the joints so that you can inspect them. In place of the extractor, you could also use a wick here to remove the solder. The first joint looks like this in cutaway. The lead is not in direct contact with the pad, and no solder bridge remains. In a case like this, a pair of diagonal cutters can be placed under the lead and gently closed, forcing the lead up. The second joint looks like this. There is a slight solder bridge existing between the lead and pad. To remove this kind, wait until the joint is cool. Then the lead can be twisted with duck-billed pliers and sheared loose. But if there's a major sweat joint remaining, as shown here, shearing should not be attempted. In cases like this, the heated tip of a thermal parting tool is very useful. It's placed on the very tip of the lead, not the pad, and once the melt is observed, the lead is lifted. Here's a similar situation. This time, the tip of a soldering iron is used, and still another, where the extractor tip is used. Once the leads are straightened, the joint is removed by the standard extraction procedure. Sometime, though, you may need to add a little more solder to the joint for good heat transfer. If you're using an extractor, a continuous method is possible, but requires greater care. You're going by feel rather than what you can see. If the component is to be scrapped, a clinched lead can be cut on the component side, and the solder extracted from the same side. The clinched lead will then come out. And here's a final component type we haven't covered, the flat pack. These flat packs are typical of planar or beam lead mounted components. The leads have been reflow soldered onto surface pads. These can be desoldered with a hot air jet, provided by a desoldering system like this one. Low pressure, heated air is forced through the tip. Its temperature is set high enough to just scorch a piece of the tissue. A thin wooden stick is used as a wedge, and the hot jet directed at each lead. The advantage is that the hot tip never touches the pad. No lifting force is applied until the solder melts, so the danger of lifting a pad is avoided. Desoldering can also be done using a small soldering iron, but you need to be very careful to use only minimum heat and pressure on the lead, or you're liable to damage the pad. One other type of lead you may sometimes encounter is the swaged lead. This type has been flattened and given a spade shape after coming through the board. It's done to hold the component prior to wave soldering. If you don't want the component, the best procedure is simply to clip the lead on the component side. Then both the solder and the lead end can be extracted. If you're saving the component, the procedure should be done this way. First, extract the joint. Then take a pair of smooth jaw pliers and squeeze it round again. The leads will now pass through the desoldered holes, and the component can be removed. The main advantage of solder extraction over other desoldering methods is its ability to remove virtually all types of solder joints. You can remove wires from terminals and leave them clean, or extract wire wrap and connector pins. And for touch-up work, it's the best way to get rid of bridging and icicles, prepare surfaces during rework, or clean up splashed solder. You'll find a full presentation of what we've covered in your handbook, so we'll stop now. Your instructor will want to review the material with you, and in the notes section of the handbook, have you write in the particular specifications, standards, and practices of your organization. Then we'll move to our next lesson, coating removal.